Do you make awesome strip board modules for your DIY synthesizer projects but are bummed about how hard and expensive it is to make great looking front panels for your sonic artwork? In this video, I'll show you how to take your front panels from looking like this to this, and it will only cost you a couple of bucks a panel. I'm Brian from EurorackDIY, and I'm here to share with you how I make inexpensive Eurorack modules that sound and look great. The main reason I wanted to do this video was to show how I make great looking front panels for my modules inexpensively using prototype printed circuit boards that you can have manufactured for you by a number of companies. Currently my preference is JLC PCB, and in this video I'll be using them for my example. I could simply show you the techniques I use for a front panel for any old module, but I figured why not go ahead and take you through all the steps to make one of the simplest of modules, the passive multiple. Hopefully with just the information I give here, anyone can quickly and easily design and build their first module. In this video series, I'll take you through the entire process from where to find information about the standards you need to follow in your Eurorack designs to what tools I use to design my printed circuit boards for both the front panels and the electronics that go behind them. I'll then show you how to submit your designs to be manufactured, and finally I'll take a look at the final product and how to assemble this simple module. Because the details of how to use the CAD software to lay out the front panel and PC board take a bit of time to explain, I've broken them out into separate videos which are linked below, and there will be links to the appropriate places in this video to them so you can pause and go watch them. Before I get into the details, I have a request. I'm just getting started with this channel, and one thing I've discovered is it takes a lot of work to make videos like this. I'm doing this mostly for fun, and I'd like to stay motivated to keep bringing you content like this. It would help me out a bunch if you could like or comment on this video so that others can find it. What else can I share that you might find interesting? Comment below and maybe I can share what I've learned. I've got a bunch of ideas about things to put in upcoming videos and breadboards full of cool circuits just waiting to be made into modules, so please consider subscribing to the channel to get notified when I create new stuff. With that out of the way, let's dig into this module. First, let's talk about what a passive multiple is. A multiple allows you to route the output of one module to the inputs of several other modules. With a normal patch cable, you're only able to route the output of one module to the input of another module. There are some patch cables that allow you to stack your connections and serve pretty much the same purpose as a passive multiple, and you can totally use those instead. We're building this module because it's the jumping off point to learn how to build a really nice looking front panel, and it's the foundation for how to create other simple, more useful modules. The passive part means that nothing happens electrically to the signals as they're fanned out. There is no power connector for this module, and laying out a circuit board to wire the jacks together is really easy. One drawback to passive multiples is that the more modules you fan a signal out to, the more likely it becomes that the combined load of all those signals changes the output signal. We won't be making our multiple with enough outputs that this should be an issue. Also, if the modules in your system use properly driven outputs and buffered inputs, the combined load should generally be less of a problem. The modules we'll design and use here on EurorackDIY will always have robust outputs and inputs. The patch cables used in the Eurorack system are mono miniature jack cables. They're also known as 3.5mm or 1/8 inch cables. They have two conductors, one to carry the signal and one for ground. The plug itself is known as a TS connector, where T is for tip and S is for sleeve. The tip of the cable is attached to the conductor that carries the signal, and the sleeve is connected to ground. For module construction, we'll need to know a little bit about how the jacks we'll be using work. There are several different jacks, and some can be soldered to circuit boards, while others can have wires soldered directly to them. There will be a connector on the jack for each conductor in your cable. For this module, I'll be using Thonkiconn jacks, which allow you to create modules where the components can be sandwiched between the printed circuit board they're connected to and the front panel. Some of the other components we'll use in other modules, like potentiometers, have similar dimensions to fit nicely into this sandwich. I'll leave a link in the description below to a couple of sources for these jacks. These jacks also have a switch in them, which we'll use later to add a bit of extra functionality to our module. When there is no plug in the jack, the switch connects a third terminal to the same connector as the tip. While this jack isn't the one I'll be using in this module, it demonstrates how the switch disconnects and connects the third terminal depending on whether or not a patch cable is plugged in. It's important to know which terminals connect to which parts of the jack, but fortunately in our case, the CAD software we'll be using takes care of those details for us. Now that we've looked at the hardware we'll use, it's time to talk about how things will be wired up. We'll go ahead and make this be the smallest practical EuroRack module. Even so, we'll have enough room to make 2 sections on our module, with one input splitting out to 3 outputs in both sections. The signal we're splitting comes in on the tip of one patch cable, and we'll simply wire that to the tips of the 3 output jacks. By convention, we'll assume the top jack of each section is the input and the 3 jacks below it are outputs. This convention will be useful when we look at how we'll be using the switch in the input jack of the lower section as a way to extend the top section input signal to also be available on all the outputs of the lower section. To do this, all we'll need to do is connect the tip wire from the top section to the switch connector on the input jack of the lower section. What this means is that when there is no patch cable plugged into the second input, all the outputs of the lower section will be connected to the first section. This turns the module into a 1 input, 6 output multiple. Let's talk a little bit about the various colors and design elements that we get from using a PC board for a front panel. We first of all have the solder mask, or the black background. We can actually get this in a number of different colors: green, red, white, purple, yellow, blue, and of course, like this board here, is black. On top of that, or the next color that we have, is the gold coloring here. That can actually be gold or silver. It's the exposed areas of the solder mask. And then finally, we also have a silkscreen color, which is white on this board. It'll be a contrasting color, so on a white board, for instance, it might be black writing. You typically don't have much choice over that, but sometimes you do, depending on the manufacturer. So looking at how these are stacked up and how the board itself is manufactured is a little bit important to understand what we're going to be doing in the CAD software where we design it. So a PC board starts with a fiberglass layer called FR4 that is what is printed on, where the circuits are put on, and the various layers of printing and stuff. And it's built like a sandwich where there's different layers of things. Their boards are double-sided, as you can see. This one here also has the solder mask on the back side. So for the sake of this drawing, all the things that I'm going to draw upwards are also available downwards. The first layer that they put on is they'll put a layer of copper plated onto the board. And this would be what carries your signals and stuff if this were an actual circuit board. They'll etch that down to have the signal traces and things like that. In the case of these boards, I build them so that they're fully copper all the way across the board, because as you'll see, that becomes important here in a moment. The next layer that they would put on after they've etched the copper and everything else is they put the solder mask. In this case, that's the black on the board that we have here. And the solder mask is typically put everywhere where there isn't a part to be soldered down, and then the open areas of the solder mask are where the parts can be soldered down. In this case, the open places from the solder mask are where the plating will show through, and so that's where the gold color comes from. And so after the solder mask is down, that will be the next layer, is what they call it, what will typically be called surface finish, is what you'll find from the manufacturers. And the surface finish, you actually have some options here too. There is HASL, or hot air solder leveling, and that will turn out to be a silver color. So if you were going for a scheme where you wanted to use a silver color for that might be kind of cool. But what this board has, and what I like to use, is something called ENIG, or electroless nickel immersion gold, with the gold being the important part. So they plate it with nickel and then gold on top of that. And of course that shows through, or the graphics for that show through, only in the places where we have not put solder mask. So it's sort of the negative of the solder mask. But that's the way the CAD software is set up too, is it sort of shows you that negative. And then finally, after you have those layers on, and those layers are put on the board, they'll do what they call a silkscreen printing layer. And that's the white lettering on top. And so that isn't a negative or anything. That is actual an actual positive image, and so then you have like one other color then that you can use to put your graphics and such in. So there's one last thing to do before we dive into KiCad and start laying out our design, and that's to do a little bit of planning around the size of the board that we're going to use, the spacing on the connectors that we're going to put on it, and some things like that. So the Eurorack standard comes from Doepfer. You can go to their site. I'll have a link below. But as you can see here, there's some key dimensions that are called out. And specifically the height of the overall height of the module is always going to be 128.5 millimeters. So we'll make a note of that. We're also going to want to know where the middle of it is, and so that, just by some simple math, we know is at 64.25 millimeters. Now, the modules themselves are done in units of HP. As you can see here, there's a table that describes the various different widths and the dimensions of them based on how many HP there are. We're going to try to make this module as narrow or small as absolutely possible. And in order to be able to get the connectors and everything on it, the smallest size that we can do is a 2 HP module. So from that, we know that the module has to be 9.8 millimeters wide. And then also we're going to want to know the halfway point of that, and that is 4.9 millimeters. So that we can lay out things on the center of that. And then finally, the thing that we need to know is the mounting holes themselves. And they have a diameter of 3.2 millimeters. So we'll make a note of that. And also the radius for that, because of the way we'll draw it out, is 1.6 millimeters. The drawing tool has us draw by radiuses. And then the positioning of those, as we notice, it's 3 millimeters up or down from the top and up from the bottom, and then 7.5 millimeters offset from the side. For modules, I don't know, less than 8 to 6 HP, there's really only room for one mounting hole. So we're going to go ahead and put that 7.5 millimeters from the left side, as it sort of shows on the dimension here. So this will be offset 7.5 millimeters. And then, as we noted, it's 3 millimeters off of the bottom, and the same for the one on the top. The next thing that we want to do is do a little bit of planning for where the actual mounting holes themselves go. And I've been playing around a little bit with it myself, and what I've been able to determine, I want to have these in 2 groups of 4. So input on top, the 3 that they 3 outputs, and then another input and 3 outputs, so the 2 groups. So I want them visually to be spaced a little bit. So 16 millimeters is about what's left here when you start looking at the spacing between them, of being about 14 millimeters, and then the same for the bottom. And then just for layout purposes, I'm going to want to know just how far they are from like where this top one is on down, and so it's 14, like the total layout. So it's 14, and then the second 14 is 28, 42. Skipping the 16 millimeters, that's 58 millimeters down to where this next one is, and then 72 for another 14 millimeters, 86. And 100. So basically what that is the offset from the center of this very first hole down to each of the successive holes after that. And with this information, we should have enough to dive into KiCad and start laying things out. One of the things I want to talk about first is the direction I'm going to place these on the board itself. As you can see, the actual housing itself has the one lead that comes out a little bit further. So the footprint for these, you can get them closer to, if you will, closer to the top if you mount them this way, or the top or the bottom if you mount this side near the top and bottom. So what I'm going to do is take the top four and mount them as close together as possible this way, the 14 millimeters, and then the bottom four, mount them as close, turn them around and mount them as close together this way. At this point, it's time to dig into the CAD software I use to design the printed circuit boards for my front panels and the electronics for the modules that go with them. As I said earlier, there's quite a bit of explanation that goes into this. So if you'd like to go ahead and pause this video to check out those videos, they're linked on the screen here and in the description below. Again, if you appreciate videos like this, please leave me a comment below and like and subscribe. Once I've laid out my front panel and board, it's time to prepare the files in KiCad to be sent off to be manufactured. Here's how I do that. So now that we have our front panel and our board all laid out, looking the way that we want it to, it's time for us to do the last step that we're going to do in KiCad, which is prepare things for manufacturing. So we'll go back into the layout tool for the panel. We'll start there. Under the file is plot, and what we're going to do is we're going to plot Gerber files. So we create Gerber files for the manufacturing process. And the plot term harkens back to the days when they actually had physical plotters that they used to draw up the various things that they needed to be able to manufacture from. I want to stick each of these in their own directory so that we know where to find things and we can zip things up and such really easily. In this case, we want to go ahead and create a new folder for this. We'll call the first folder, since we're working on the panel, panel.gerbers. And select that as the place that we want them to go. Yeah, sure. Go ahead and click plot to generate all the files. Basically, the defaults that are set here are what you're going to want. You're going to want the copper files, the pastes, for the solder paste, the front and back silk masks, or front and back silk screens, front and back masks, and the edge cuts. So when we click plot, it goes ahead and creates those. And then we also have to provide drill files. In this particular case, I don't believe that there's anything that's going to get drilled on the front panel, but we'll go ahead and do that too. We want to make sure that the output is set to be the same place. It's a little bit wonky. We can see that it's actually panel Gerbers, and we'll go ahead and say generate drill file from here. And it's done that, and so we can go ahead and close that. And close this out. So we're going to go ahead and open a file explorer in the directory that our project is stored in. As you'll notice here, we have panel Gerbers, which is where we saved all those files that were out, and then the two drill files and all the Gerbers. And what we need to do to be able to submit them is we need to put them all into a single compressed archive zip file, if you will. So we'll select all of the files, right-click on them, and send to a compressed zip folder. And let's give it a better name. We'll just call it panel.zip. And they should all be there ready for manufacture. Now we simply go back and do the same steps for our other board. So go ahead and open up board.kicad. Sure. File plot. Again, let's create a new its own output directory for it. This one we'll call board. Click on plot to get the files there, and then also generate drill files. Make sure that it's still in board Gerber. Generate the drill file. This one, it does matter because we do have all the holes that that we're going to be mounting our parts into, and we can close that. And again, switch to File Explorer and go into board Gerbers. Grab all the files, send them to a zip folder. Let's call this board.zip. That's it. So one more step left before we get our boards back in hand is we have to send them to the manufacturer. I use JLC PCB. There are a number of inexpensive manufacturers out there these days. This one just happens to be the one that I've learned and know how to use and know what kinds of options I have. They have SMT assembly, which is really nice when we make boards that have actual circuits on them, and we can lay things out and have them partially assembled with SMT components on them and placed on them and all built up and stuff. But we'll start out at their homepage. I'll leave a link below also. But you're going to click on the button to get Quote Now. It'll open you up a new tab. And right away, we can go and we'll start by adding our Gerber files that we have. We'll work on the panel first. And from here, we'll go ahead, double click into our panel.gerbers and select panel.zip, the zipped up archive files. JLC PCB uploads them and processes them to make sure and see that everything on it is what they expect. This is pretty cool because now you can see that you see the representation of it. We don't want them in green. I don't want them in green necessarily, but it does show that there's the front and the back of the board in their viewer. And now we go ahead and select the options that we're going to have. A lot of times it's able to figure out the dimensions from the Gerbers. For some reason, this one doesn't seem to. We happen to know that it's 128.5 by 9.8 millimeters big. You can order them in quantities of 5s or on up. In this case, I'm just going to get 5, but if you wanted to make more or have bigger runs, you could do that. There's just this one design that's on it. We're going to go ahead and have it be delivered as a single PCB. We're not using any of the panelization or any of those kinds of things. The PCB thickness is 1.6, and in this case the color is black. And as we said, as you can see, it's starting to calculate the price over here. And because it's a little bit bigger than their standard 100 by 100, we sort of get out of the absolute least expensive layer, and that's why now we have an engineering fee, but it still is pretty inexpensive. But this next option here is what gives us the most cost, and this is the ENIG coating that we want on it, the electroless nickel immersion gold coating, so that we get the gold text. As you can see, that adds a fair amount to it, but still $20 for 5 of these boards seems like a really reasonable price. $4 each for getting these manufactured. And then the copper weight and these options we don't actually care about. And we did talk about this one though, is remove the order number. And we do want the order number there because otherwise it might end up on the front of the board where it would show up on the front of our panel for the front panel specifically. We're going to say specify a location, and this is the one where we talked about that that we put the JLC text on a place, and they're going to put their order number overlay it on that place where we've put that. For the front panels, I actually like to leave a remark because they do check these boards and it might end up having somebody look at it and wonder where are these circuits or how are these circuits connected together. And since it isn't actually a functioning circuit board, I will typically leave a remark here that just says something to the effect of, this is a front panel and has no electrical connections or something. And that's basically all we need to do for our front panel, and we can save that to our cart. And now we get to see it in the colors that we've selected for it and everything, and that looks just fantastic. I always love this part when you get to see the final thing. You can click on the Gerber viewer. Takes a few moments. This is also good to do when you're getting boards manufactured, you're getting parts, surface mount parts placed on them and such. But that's our board. Going back, we want to go ahead and add another item because we want to get our actual circuit board manufactured. So we can go ahead and add another Gerber file. In this case, we want to go to the board and get the board.zip. So again, it's detected a 2-layer board. Now, we only laid things out on the front, but it's also, because the pads go all the way through, they're also plated and there's a solder mask on the back of this board, even though we didn't do anything to lay it out. So it is still a 2-layer board. It does know the dimensions of the board in this particular case. And as you can see, the price now back down to $4 and for this particular one. The options are all pretty much the same. It's still a single PCB 1.6. I just left mine when I sent, in this particular case, I just left it green because it's standard PCB color. But again, if you want to play around with this one, it won't show because it's the panel that's behind, and so when you have all your modules in and stuff, you won't actually be able to see this. I go ahead and leave the hot air solder HASL with lead. It's a little easier to solder to. It's also the cheapest option. It's not a ton more if you want to go to the lead-free version, and you don't really need the gold plating for this. It's useful for boards if you're going to leave them around for a while because it doesn't tarnish or build up any sort of surface sort of thing, so it stays easier to solder if you're going to leave them around. But to keep things inexpensive, we're going to go ahead and leave that there. Also, we don't need the order number. We don't need to remove the order number, and there really isn't anything to leave for a remark on this. So we're totally ready to save it to our cart. And now we can see it, and we can also bring it up in the Gerber viewer. Just to go ahead and check it. And everything looks right by it. You can also turn it over and look at the top and the front and the back with some things there. So back to the tab. So this is basically everything in the cart. We'll go ahead and select, before you send it out, you want to make sure you have everything selected. But short of shipping, $25 for these 5 boards. So basically what we're at is $5 worth of PC boards for this module. There's the 8 jacks that we have to have, which are another at about 50 cents each. Is another $4. So $9 again without shipping factored in there. But shipping, there are some very inexpensive options for that too, depending on how long you're willing to wait for it. And but anyway, so $5 each for each pair of boards and $4 worth of connectors. You're under $10 each for these modules, and I think that's a pretty fantastic price to be able to get them. So from here, right, you go ahead and do everything you need to do to check out and get to wait for your boards to come in. I'm going to go ahead and wrap this video up here. In the fourth and last video of this series, I'll show the boards I got back and how to assemble them into a module. Thanks for watching, and I hope the information I shared here was useful. Like I said earlier, it will help keep me motivated to make more of these videos if I know people are watching them and finding them helpful. You can help me out by leaving a comment or a like and sharing with friends who might also be interested. Also, please be sure to subscribe so you won't miss any future videos I make.